Majersky today from the ATLAS collaboration. He did his PhD in 2020 in Bratislava, working on the charge asymmetry in 𝑡𝑡 bar production. Then, a bit shortly later, he moved to Zeuthen as a postdoc and has, in the meanwhile, been a top cross-section convener. In addition to his analysis work, he works on luminosity and also on the top-related software frameworks. Today, we hear an update on the top-quark with top precision, and the floor is yours.
Okay, thank you very much. So it's my pleasure to give this seminar, and actually it's kind of funny that it is a nice opportunity because this year actually is the 30th anniversary of the discovery of the top quark, and the picture that you can see here is from the mini celebration we had at the top conference, which took a little over a week ago in South Korea, in Seoul. So I'll begin with a short introduction. I mean, so like I said, the top quark was discovered 30 years ago by CDF and D0 experiments at the Tevatron, which was a proton-antiproton collider in Fermilab in Chicago, US. With its mass of 173 GeV, approximately, it's the heaviest elementary fermion, with a top quark Yukawa coupling of roughly 1, which means that the top quark plays an important role in the electroweak symmetry breaking mechanism. And one of its unique properties is that it has an extremely short lifetime that's actually 2 orders of magnitude shorter than the hadronization time, which means that the top quark decays before hadronizing. So we have the possibility to study properties of a bare quark. And the other nice thing is that thanks to the CKM matrix elements, it practically decays exclusively into a WB pair. So you know that your final state is a WB, and your final state is purely determined by the decay products of the W boson. Now, at the LHC, we have a large range of processes involving top quarks, going all the way from 𝑡𝑡 bar to single top-associated production, all the way down to 4-top production, spanning around 5 orders of magnitude in cross-section. But in this talk, I will focus on 𝑡𝑡 bar production. So at 13 TeV, with the cross-section of roughly 830 picobarn, the LHC is a top quark pair factory. And if you take the run to luminosity, we basically have something like 100 million top quark pairs produced. So plenty of statistics for precision. As you will actually see, both the results I will show are limited by systematic uncertainties. And at the LHC, the dominant production for the 𝑡𝑡 bar production is gluon fusion. So at the bottom of the slide, you have 2 example diagrams at tree level for 𝑡𝑡 bar pair production in the S channel and T channel. So I'm going to present 2 results in this seminar that are really very new because they were basically made public shortly before the top conference or at the beginning of the conference and shown for the first time in Seoul. So the first measurement is the measurement of inclusive and differential leptonic cross-sections in 𝑡𝑡 bar events in the final state with electron and muon in the lepton channel. And the second measurement is the measurement of the top quark Yukawa coupling in 𝑡𝑡 bar events, this time in single lepton final state. So I'll start with the first measurement. And I'll say a few words about the motivation and current status. So why do we want to measure inclusive cross-sections? Well, first of all, it's the test of perturbative QCD predictions, where our current state-of-the-art is next to leading order QCD with next to leading log resummation. And you can see actually in the plot on the right-hand side, this shows the comparison of the theory predictions. That's the blue and green line, which show for Tevatron and for LHC as a function of center of mass energy, square root of S, and compared to all the inclusive cross-section measurements done by ATLAS and CMS over the years. And you see when you look at the ratio plot that there's a pretty good agreement with the state-of-the-art predictions with the measurements. The second point is that one can also extract the top quark pole mass from the inclusive cross-section, and the pole mass extraction is kind of the theoretically cleanest approach to extracting the top quark mass. And So the previous most precise measurement, which was done at 13 TeV, was also done by Atlas in the EMU final state. And you can see it when in the zoom in ratio, it's actually this blue square where you can barely see the error bars protruding out of it. Sorry. And in this measurement, okay, you see it's in perfect agreement with the theory. This measurement already had an impressive precision. The uncertainty on the cross-section was 1.8%. Now, the measurement was limited by systematic uncertainties. You can see the full breakdown in the table on the right. I'm not going to go in the full list, but just to say that the most important ones were, of course, signal modeling. That's kind of a long-standing evergreen issue with TT bar. The knowledge of lepton efficiencies, since this is in dilepton state, and the luminosity uncertainty. So this new measurement employs a similar strategy. I will go over the details in a bit, but also includes several improvements and additions compared to the previous analysis. So what's the idea in this measurement? Okay, so as I said, we select events in data with an opposite sign EMU pair. And we use this so-called B-jet counting method where we count the number of events in data with having exactly 1 and exactly 2 B-jets. And you can see the B-jet multiplicity data Monte Carlo comparison in this plot on the right-hand side. And then the problem is formulated with this set of 2 equations shown here, where let me start with the second equation. So the general idea when you want to do a cross-section measurement is that if you count the events in data, this should be equal to the number of signal events plus background. And the signal you can express in terms of the integrated luminosity of the data set times the cross-section times whatever efficiencies that basically limit the number of events you have. And in this B-jet counting method, the efficiencies are parametrized using 3 parameters, 2 efficiencies specifically. First is the epsilon EMU, which is the dilepton selection efficiency. So this is efficiency to reconstruct and select the 2 leptons with the selection criteria that we have without any requirements on B-jets. And then we get a second term expressing the efficiency of reconstructing jets, identifying them as B-jets, and selecting them. So if we look specifically at the second equation, N2, the B-tagging efficiency factor is this CB epsilon B squared, where the epsilon B is a probability to reconstruct a single jet, identify it as B-jet, and this is measured in data, actually. Now, if you require 2 B-jets, then this is probability squared. That's where the epsilon B squared comes from. But there is also this correlation factor CB because the two, like identifying 2 B-jets in the event, this is not a fully statistically independent case. There are some small correlations. You can see the factor is very close to 1, but not exactly 1. And if we look at the equation N1, so this is for counting events with exactly 1 B-jet, then you get this factor 2 times epsilon B times 1 minus CB epsilon B, which basically expresses that you have the chance to select 1 out of 2 B-jets, but then you get a factor for the fact that events with 2 B-jets migrate to the N2 bin instead of the N1. So summed up in total, you get a system of 2 equations with 2 unknowns. You simultaneously measure the cross-section and the epsilon B in data. And the nice thing about this method is that then the systematic uncertainties will impact the correlation factor, the epsilon EMU, the leptonic efficiency. Of course, background yields and luminosity uncertainty impacts luminosity and the backgrounds. But the nice thing is that in terms of your signal, B-tagging and jet reconstruction uncertainties get absorbed in this epsilon B. So this is how you reduce the impact of those uncertainties. So a few words on event selection. First, I mean, I already mentioned that, okay, we have a final state with 2 leptons. We select the events in data using single lepton triggers, which, depending on the year of data taking in run 2, this limits our leading lepton PT selection ranging from 21 to 27 GeV. Compared to the previous analysis, we have a more relaxed selection for the subleading lepton of PT of 20 GeV, which helps us increase the acceptance and then therefore reduce a bit extrapolation uncertainties. We reconstruct jets using standard Atlas procedures. So we use anti-KT algorithm with radius parameter 0.4 with PT above 25 GeV, and we use this machine learning-based DL1R algorithm to identify the B-jets. Now, regarding signal modeling, what I like to point out, this was one of the issues with the previous measurement, and it's kind of a long-standing challenge in TT bar measurements, is that our current standard Monte Carlo simulations for TT bar are all based on next to leading order QCD, which we know predicts harder top-quark PT spectrum than in data. And this, by definition, extends to mismodeling also of the decay product. So what is shown in the plot on the bottom right is the distribution of mu1 PT in the mu plus 1b selection region. And so this is a comparison of data with several Monte Carlo predictions, which are shown in the bottom. So I would like you to focus first on the dashed and dotted blue and red lines, which are this Pauek PTR and Pauek Herwig, which are next to leading order QCD predictions in production. And you see that when you look at the ratio of prediction to data, there is a clear slope. And this impacts the inclusive measurement through acceptance effect. Since you require some selection on the PT of the leptons, you get an uncertainty when you then measure the total cross-section through the extrapolation effects. And there is an intrinsic uncertainty on the lepton PT mismodeling because of this slope, and this was one of the dominant uncertainties in the previous measurement. So the improvement that is done in this analysis, this is the first top analysis that uses Pauek MinLo plus PTR8 Monte Carlo as baseline, where the MinLo has next to leading order QCD accuracy and matrix element matched to Parton shower. And you can see in the ratio that is the black line that it has a significantly better lepton PT modeling. So it actually eliminates the corresponding uncertainty that we had before. Of course, there are uncertainties on this prediction that cover this. But in general, the other benefit is that we get also smaller modeling uncertainties related to radiation, especially because the scale variations at next to leading order are smaller. And I will show you this when we get to the results with the uncertainty breakdown. A few words on background estimation. So if you look at the table on the top right, in general, this analysis has rather small background contamination, and in the 1 B-jet region, it's around 12%, and in the 2 B-jet region, it's 4%, so quite small. The dominant background is the single top TW production, which we estimate from Monte Carlo, and we normalize it based on theory predictions, followed by misidentified leptons, Z+jets, and diboson, which are like order of magnitude smaller. So these are very, very small backgrounds. For the misidentified leptons, so this is basically fake leptons or non-prompt leptons, such as from heavy flavor or decays. We use a same sign selection to basically select same sign selection to predict the rate of the opposite sign in the opposite sign region. So the idea basically is you take the same sign region, which is heavily enriched in fake leptons. You subtract the contribution of processes having 2 prompt same sign leptons. And then you need a transfer factor basically to get the prediction in the opposite sign region. And you do this differentially in bins of whatever distribution that you're looking at, essentially. The important point is that the ratios we use from the simulation, but we check that basically we trust that the Monte Carlo simulates this well enough from the tests. And finally, for the Z+jets background, this is basically coming from Z2 tau-tau decays, where both the taus decay leptonically, giving us the electron-muon in the final state, in addition with heavy flavor jet production. This background is estimated also from simulation, but we know that the Z+ heavy flavor rate is not predicted well, so we actually normalize this from data by fitting MLL distribution in the Z2E and mu events to obtain a normalization factor with an uncertainty. So I already covered a bit about the signal modeling, which is one of the challenges in this measurement. Now I will talk a few more words about two other big categories of uncertainties that are important in this measurement. So first is lepton modeling uncertainties, since the lepton-related efficiencies directly impact the epsilon mu parameter, and through there we get the uncertainty. So it's essential to measure these precisely. So for the reconstruction and identification efficiencies for leptons, we traditionally measure these using tag and probe approach in Z2e and Z2mu events. And we actually get an order of magnitude of 0.1% uncertainty per each lepton on the epsilon mu. And the second important category of lepton-related uncertainties is the isolation efficiency. And this is something where we know from past experience that the TT-bar Monte Carlo simulations are known to not model this very accurately, or not with a sufficient accuracy for this measurement. So actually, there's an in situ measurement in TT-bar EBU plus greater than 1B events measurement done in this analysis. You can see the measurement in the plots on the right-hand side, where the top plot shows the electron isolation efficiency, bottom plot muon isolation efficiency, as a function of the lepton PT in two bins of eta. And you see that actually at low PT, the electron isolation efficiency is slightly underpredicted by roughly 1.5% for the TT-bar min-low plus PTR 8, so the baseline sample. And for muons, it's the other way around, that the efficiency is overestimated by 1%. So we calibrate this using this in situ measurement, and again, we can do this with a precision of roughly 0.1% per lepton. And finally, the trigger efficiency uncertainties, since we trigger on the leptons, these turn out to be negligible. This is thanks to the fact that actually most of the events get triggered by both leptons, so you have a redundancy there. Okay, and then the final bit about uncertainties that I want to talk about is the treatment of luminosity uncertainty, aka how to improve an already very impressive uncertainty. So the luminosity uncertainty for the full Atlas run-to dataset is 0.83%. The way this is obtained is actually we have the uncertainties for individual years of the data taking, and then in the combined uncertainty, the 3 years of data taking, the events are weighted equally. But we see from the table that for the 2015 plus 16 data, the luminosity uncertainty is slightly better than for the following years. So the idea is that why don't we measure the inclusive cross-section separately for the 3 sub-periods of the run-to data taking, and then we combine them using the blue method. And this is exactly what is done in this measurement, in this updated analysis. So that brings me to the results. So first of all, the final measured cross-section in this analysis is 830 picobarn, which is in very good agreement with the state-of-the-art standard model prediction. You can see the new measurement shown in this plot in the ratio panel. So this point that has very small uncertainty is the updated result. And you have for reference all the Atlas measurements here for the different center of mass energies. And finally, what I'd like to point out is actually this table at the bottom. I apologize, there's a huge number, list of numbers here. But just want you to focus on 2 rows. So the first row, this is if we analyze the run-to data set all together. So single analysis of the full data set. And then we have the blue combination. If we analyze the inclusive cross-section in the 3 subperiods, and then we perform the combination, and you see that actually we get a slightly better luminosity uncertainty, 7.3 versus 7.6. And one final word that I didn't mention, but when you look at the uncertainty breakdown, we've reached the point where basically the systematics and the luminosity are on par. And we also estimate the uncertainty on the beam energy, which is rather small here. It's 1.9. So how do the systematic improvements actually give this result? So what I show here in the 2 tables is the comparison with the uncertainty breakdown for the previous analysis and the current one. So as I already mentioned, the top PT reweighting uncertainty is gone thanks to the fact that we switched to a next to leading order QCD prediction. The uncertainties related to radiation are also reduced thanks to this transition. And then finally, the lepton efficiencies are significantly improved as well. And we get also a small or modest increase in the precision of the luminosity thanks to the blue combination. So how does this stack overall? You can see in this table here where we compare the relative uncertainty for the total and fiducial cross-section between this analysis and the previous one. And you see that we now achieve 1.34% precision. So it's really unprecedented. I also mentioned that you can actually extract the top quark pole mass from the inclusive cross-section because the cross-section depends strongly on the value of the mass. And you can see this in this plot where the red curve with the cyan band shows the dependence of the predicted cross-section, thermal cross-section, as a function of the top quark pole mass. The horizontal dashed line shows the measured cross-section value. And then these black points actually show that the measurement itself has a small dependence on the assumed top quark mass in the Monte Carlo. This is basically coming from acceptance effects because the change of the mass changes your kinematics, but this dependence is much smaller compared to the actual measurement one. So then when we look at the results of the extracted mass, we have results for two different PDF sets. So first is this NNPDF 3.1 no top, which basically does not contain any data from LHC measurements, including TT bar cross-section, to basically avoid a sort of a circular dependency where you use top measurements already in the PDF set. And you can see that the mass 0.8 GeV is already limited by theory uncertainty. So the experimental component is just half a GeV. We also have a result for an older CT14 PDF set for reference, because we can then compare this with the previous measurements of the pole mass from inclusive and differential cross-sections. And in particular, the first three measurements here are from previous measurements extracting pole mass from inclusive cross-sections. And you can see that the measurement is in good agreement with those, and actually it is the most precise pole mass measurement to date from an inclusive cross-section. So that brings me to the differential cross-section measurements, where essentially in this analysis we specifically target lepton differential cross-section, so in terms of lepton observables. And here we can actually naturally extend the B-jet counting method from inclusive measurement to a differential measurement. So if you take some observable such as lepton PT, you just get the set of equations for every single bin of the observable. You again measure simultaneously in data epsilon B and the cross-section for each bin of the observable that you're looking at. And there is one slight change, that the epsilon E mu parameter, the efficiency, dilepton efficiency gets swapped for this G E mu I, which is the per bin fiducial efficiency. So it's basically the probability that the event at fiducial level passes our reconstructed selection. And the fiducial region is defined by requiring the electron-muon pair with a lepton PT above 20 GeV, and there are no requirements on jets here. There is one challenge with the measurement defined in this way, which is that if we look in certain regions of kinematic phase space, such as, for example, at the tails of the lepton PT, so this plot shows you the relative uncertainty of the measured differential cross-section as a function of lepton PT. At very high PT, the uncertainty is up to 10%, and you see it's completely dominated by background, and specifically by the modeling of the TT bar and single top TW interference, or TWB actually at the NLO. So this comes from the fact that traditionally we simulate TT bar and TW as independent processes, but at next to leading order, you get contributions of this TW production with a B-jet, where when you look at the two diagrams, okay, TT bar is basically doubly resonant, and then single top TW have singly resonant, you get the same final state. So basically there is an interference between these diagrams that you should take into account. But since we simulate these processes separately, we have approximate treatments for this, which either we use the so-called diagram removal or diagram subtraction approach. And since this is ambiguous choice, and theoretically both are actually wrong, we take the difference as a systematic uncertainty. The proper solution would be actually to simulate the full WB final state, which I will get to in a bit. So what is new in this measurement is, in addition to the differential cross-section in TT bar E mu, we also perform a differential cross-section in E mu BB phase space, where we treat TT bar and single top together as signal. So how is this done? So first of all, the fiducial space is then defined using the same lepton requirements as before. But in addition, we require 2 B-jets with the requirements listed here. So you no longer distinguish what is in the middle of the process. You just assume that you have the full E mu BB final state, and anything that's in between contributes. So again, we measure the cross-section only in bins of leptonic observables. And in this case, we cannot use the B-jet counting method. So instead, we revert back to a simpler way how you measure the cross-section, which is basically that your number in data is proportional to signal plus background, where signal is just luminosity times efficiency times the cross-section. So when you express this, you get this term here, where, again, the G is the E mu BB fiducial efficiency, similar to as in the previous measurement. But there is this correction factor S-tag squared here, which is equal to the epsilon B, so the B-jet efficiency in Monte Carlo divided by B-jet efficiency in data. And this is taken from the inclusive measurement. So you calibrate your B-jet efficiency, the inclusive value, and you also reduce absolute normalization uncertainties thanks to this, but it's not per bin, so you don't correct for some shape effects in the B-jet mismodeling, basically. And in this way, when you take the E mu BB final state, the background is only 0.4%, because you're left basically with the Z plus jets and fake leptons. So you have a very pure inclusive sample then. And just to give you sort of a glimpse of a comparison, so if we take these 2 differential cross-section measurements, you can actually see that in the E mu BB differential measurement on the right-hand side, same observable, lepton PT, and the breakdown of the relative uncertainties on the E mu BB cross-section, you see that the uncertainty is much smaller, so it's only 4%, and it's actually limited by data statistics and TT bar modeling, so it's more precise. But the downside, quote unquote, is that here you combine TT bar and TW. So when you compare the Monte Carlos, you have to somehow combine them together to compare with this differential cross-section. So that brings me to the results. And I know that there is a lot to uncover on this plot, so let me walk you through it. So first of all, the plot in the middle shows the absolute differential cross-section as a function of lepton PT, and both the differential measurements are presented in the same plot. So first of all, you have the filled black points with the cyan bands. That's the TT bar to E mu measurement. And then the open points with the orange error bands, that's the E mu BB cross-section measurement. And now we have several classes of predictions compared in this ratio plots. I would like you to focus first on the first 3, where always the data measurement uncertainty is shown with this colored band, so in this case, the cyan band. And so in the first ratio, we have a number of Monte Carlos, which are next to leading order QCD production, and they use narrow width approximation for decay. And you can see that basically with different level of accuracy, but still most of them cannot describe the lepton PT slope very well. Some generators such as AMSIT and LO and PAWEG-RIC7 do a little bit better than PAWEG-PTA, but still. There is also a comparison of several different PDF sets performed with the PAWEG-PTA 8 in the second ratio, but you see that basically they don't really matter that much. And then the third ratio panel is the interesting one. So this shows you the next to leading order QCD-based predictions, again, still using the narrow width approximation in decay. And you see that the next to leading order QCD-based predictions agree much better with data than NLO, so that the slope is basically reduced. So that's PAWEG-MINLO with 2 different PDF sets, and there's also PAWEG-PTA using fixed order next to leading order QCD prediction reweighting applied. And then the final ratio panel shows the comparisons of Monte Carlos with the EMU-BB differential cross-section. So here it's a little bit more complicated. This is EMU-BB. We have points for TT bar at next to leading order and next to leading order in production, together with the TW single top either using DS or DR, which is next to leading order QCD in production. So there you have the black points, that's POWEC PTR8 with DR, and you see that there is a huge mismodeling in the slope. And then we have the POWEC min-law samples combined with single top either DS or DR, and you see that they agree better with the data. And finally, in this measurement, we also have the POWEC BB4L, which is a simulation of the WB final state that is next to leading order in QCD in both production and decay. So it also agrees better with the data than POWEC PTR8, because in the tail of the lepton PT, you also have effects from the interference that the standard POWEC PTR doesn't describe so well. I will flash one more result. Of course, in the paper, there are many more distributions, so I just pick a subset. So this is the lepton-eta differential cross-section measurement. And here, if we look at the ratios, the one thing that is kind of common everywhere is that data seems to be more forward than the predictions. Some of the PDF sets improve this slightly, such as CT14. And then we also see that both POWEC min-law PTR8 as well as BB4L in the EMU-BB agree a bit better than our standard next to leading order QCD workhorse Monte Carlos. So that brings me to the second measurement in my talk that I want to talk about, which is the measurement of the top-quark Yukawa coupling in TT bar events with the single lepton final state. First, a little bit of motivation. So in the standard model, the coupling between the Higgs field and the fermions, except the neutrinos, is described by the Yukawa coupling. We all know this. I already mentioned that the top quark has the largest Yukawa coupling, expected to be 1, so GT equal to 1 with its mass. And when we want to test the consistency of the standard model by measuring the Yukawa coupling, I mean, typically analysis measure this coupling modifier, which is the ratio of the measured coupling to the one when you assume that standard model holds, that basically this relation between the Yukawa coupling and the mass is linear. Sometimes I point out that sometimes it's referred to as kappa F or YF, because in the analysis we use the latter one. And there are several approaches how to measure the top Yukawa coupling. I'll give a very, very brief overview of these. So first of all, we can measure the top Yukawa coupling in the single Higgs boson production through the gluon fusion channel, which is the dominant production mode for Higgs at the LHC. And you see that here, actually, if you look at the Feynman diagram, the Higgs enters through this fermion loop. So you get, in principle, all the fermions, but the top quark gets the largest weight thanks to its mass. You get the Yukawa coupling here in this vertex. The limitation, quote unquote, of this method is that you have to assume standard model couplings of the other particles. Basically, that there is no BSM here. Then we have the direct measurement using TTH and TH. Direct because you get access to the Yukawa coupling right away at the tree level. This process only constitutes 1% of Higgs production at the LHC, and even order of magnitude less for TH. So it's very rare. And then we have two additional indirect approaches possible. So the first one is extremely rare, is through the four-top production process, where the dominant amplitudes are basically fully in QCD, but you can also have diagrams where one of the top pairs is produced by radiating a virtual Higgs boson. And then finally, in this analysis that I'm going to present, we extract the top Yukawa coupling from TT bar production, where the Yukawa coupling enters through electroweak loop corrections. And here we leverage the fact that TT bar is very abundant, but of course the downside is that, the modeling is challenging, as you will see. So if standard model holds, all these approaches should yield basically top Yukawa coupling consistent with standard model. But if there's BSM physics present, then in principle, the BSM physics could affect the different approaches differently. So there is motivation to measure all these in terms of complementarity. So what's the impact of the electroweak corrections on TT bar? So the electroweak corrections that we consider here, the lowest order ones, come from an interference between the Born amplitude, which is shown here, and an amplitude including the electroweak loop corrections, where you can have a Higgs exchange. So this gives you corrections of the order of alpha s squared, yt squared, where, as a reminder, here by yt I mean the coupling modifier. And this is just a representative example for the S-channel gluon fusion. You will, of course, have additional amplitudes in T-channel. And then when we want to see what is the magnitude of this correction, so we actually computed the corrections using Hathor. So in this plot on the bottom right, we have the ratio of the electroweak cross corrections. So this is basically the difference between the cross-section involving the electroweak corrections and not involving, over the leading order QCD cross-sections. This Hathor is leading order in QCD. And you see that the corrections get substantial in the TT bar production threshold, where the two top quarks are at rest, so the invariant mass is proportional to the mass of the 2 times the top quark. And you can see for the different values of yt that there is a substantial effect. For yt equal to 2, you get up to 20%. So the sensitivity of this measurement, as I will show, is not competitive with the direct measurements, which achieve something like order of 10%. But here we are potentially sensitive to BSM loop contributions, which could impact these corrections. So there's complementarity to other indirect approaches. So what's the analysis strategy? So as I mentioned, we target the single lepton channel, in either requiring 1 electron or muon in the final state. We use single lepton triggers, where we go with lepton PT above 27 GeV. We use, since we have single neutrino in the final state, the even reconstruction is more easy compared to dilepton channel. That's why we started with this final state, actually. So we reconstruct the full TT bar final state, then to get the TT bar invariant mass. And we then construct templates for different value of yt, and I'll explain how we do this using the electroweak corrections. And then we extract the Yukawa coupling through a template morphing profile likelihood fit using these templates. So regarding the event selection, since this is single lepton channel, we expect to have 4 jets in the final state, so that's what we require, and 2 of them should be B-tagged with exactly 1 electron or muon. And we have additional criteria that I'm not going to go into detail, but we use them to basically suppress the contribution of non-prompt and fake leptons. And then we proceed with the event reconstruction, where we first reconstruct the hadronic top decay. So we find the pair of light jets that yield the W boson mass, and pair the W boson jet then with one of the B jets that should yield us a top mass. And then we proceed to reconstruct the leptonic top decay using the lepton, missing transverse energy information, and the leftover B jet. And we, since you have the ambiguity in the neutrino PZ reconstruction, we determine this from the constraints on the W mass. We take the solution that yields the mass closer to the leptonic top mass. Now, in addition, we put additional cuts on the reconstructed mass of the top quarks and the hadronic W mass, because this helps us to reduce the bias in the reconstructed MTT bar spectrum. And you can see this in the plots here, where the left plot shows the resolution of the invariant mass. The blue dotted line shows you the resolution with no selection imposed on the MT and MW. And you see that there is this long tail, which if we impose these selections, we get a more symmetric resolution and also reduced bias. And the right-hand side plot shows you a correlation between the reconstructed mass of the TT bar system and the mass at the parton level from simulation. You see that there is a very nice dependency, linear dependency here, basically, with no apparent bias. So then how do we construct the YT-dependent templates? So in this analysis, we still use the NLO QCD-based POWEC plus PT8 sample. And since we have the next to leading order electroweak corrections from Hathor, we parameterize these, or we have the predictions as a function of the TT bar invariant mass and the scattering angle of the top quark in the TT bar rest frame, or the cosine of it, this cosine theta star. And so for each event in the simulation, we assign this weight, this 1 plus delta electroweak, which is a function of the yt squared. Now, because these corrections are exactly linear in yt², we use yt² as the observable in the fit instead of yt, because this means we get a nicely Gaussian likelihood. And you can see what this looks like on the plot on the right-hand side. This is an example for the invariant mass spectrum at detector level for the muon channel. And you see how the spectrum changes for the different YT templates. Here is the ratio is with respect to yt² 1 template. And you see that we have also these templates with negative yt². These are purely unphysical. They're just there to stabilize the fit. And the way we do this is because the electroweak corrections are linear in yt², you can trivially extrapolate them to negative values. And you can see this in these 3 plots at the bottom, which are examples from 3 bins of the distribution, how the yield in the bin changes as a function of yt². So we have templates for a few discrete values, and you see that there's perfectly nice linear dependence here. So a few words on signal and background modeling. Signal modeling I already talked about. Most of our backgrounds are modeled using simulation, with the exception of fake leptons, where we use this data-driven matrix method. But I won't go into detail because the fakes are very subdominant. In fact, because we have 2-BJet requirement, the total background is just 6.5% of the total expected yield. And you see in these plots that it's dominated by single-top TW production, and then followed by W+jets in the red. Now, because we're studying the threshold region, and I should point out that in these plots, this is the pre-fit data Monte Carlo comparison, okay, for the invariant mass in the electron and muon channel. And then we actually simultaneously fit these 2 regions to extract the yt². I want to draw your attention to the threshold region, where we know that we expect, based on the recent developments, we expect enhancement in the cross-section from these quasi-bound state effects, commonly referred to as toponium. And we include this using a simplified model from Maltoni and the collective, which treats this toponium as a pseudoscalar resonance, which has the mass of the 2 top quarks minus 2 GeV for binding energy, and the width is tuned based on non-relativistic QCD predictions. And we treat this toponium as a background process because, as a matter of fact, we do not know, we do not have electroweak corrections for the toponium, so they are obviously not applied. So we do not correlate this with signal, but treat it as background. But we've done extensive tests with different assumptions about the toponium model and found out that it's actually not, is a very subdominant effect in this analysis, surprisingly. So that brings me to the results. So from the profile likelihood fit to the 2 regions, we extract yt² with the value of 1.3 plus minus 1.7, which is consistent with the standard model prediction. And then we proceed to calculate the 95% CLS upper limit. So we get the upper limit trivially for yt². Actually, you can see on the plot on the right-hand side the likelihood scan with the unphysical region, which the CLS method automatically takes into account, that we basically exclude the unphysical region. And then when you have the limit on yt², it's trivial to obtain the limit on yt. It's just the square root. And here I implicitly assume, I mean, I speak of yt, but we of course mean the absolute value because we're not sensitive to the sign of the coupling modifier here. And in the table, you get the results for expected and observed yt² and the expected and observed limits for the individual fits and also the combined fit. And so we get an upper limit of yt less than 2.1. So how does this compare, for example, to the 4-top production? The 4-top production in Atlas had an YT limit of 1.7 expected, less than 1.7 expected and less than 1.9 observed. So it's slightly better, but we're this measurement is in a similar ballpark. And as I mentioned, the measurement is limited by systematic uncertainty. So on the plot on the right-hand side, I don't want to go into all the gory details. This is the impact of the individual uncertainties on the yt² extracted from the fit. But just to say that when you look at the dominant ones, these include mainly TT-bar modeling and jet energy scale contributions. So that brings me to my summary. So I've shown you two new results, very new results that were shown in the top conference. So the first is impressively precise 𝑡𝑡 inclusive and lepton differential cross-section measurement. It's the first Atlas top physics measurement that uses the Powell-Heck-Min law as the baseline Monte Carlo simulation, and we hope that we will have more results adopting this Monte Carlo, but there's still work to do. It also includes the most precise pole mass measurement from inclusive 𝑡𝑡. And hopefully the differential cross-sections will serve as an input for future 𝑡𝑡 modeling refinements. And the second measurement I showed is, again, first time that Atlas measures the Yukawa coupling in the 𝑡𝑡 production threshold, where we measure YT squared well compatible with standard model, and we estimate the upper limit with comparable sensitivity to the extraction in the 4-top final state. And I mean, as I mentioned, this result is complementary to other direct YT measurements. So that's all from my side. Thank you.
Thank you very much. So that's indeed a very impressive plot here, summarizing the precision you have reached. The floor is open for questions. Michelangelo.
Thank you. This is really impressive, of course. I have a curiosity. We know that the single lepton final state and the dilepton final state, they have the same rate, okay? And we can calculate, it's just the branching ratios. So if you were to measure this ratio, you would remove, say, luminosity, all of the theoretic, part of the theoretical, at least modeling systematics, and you would be left with systematics like the lepton efficiency, maybe bit tagging. So some of the experimental systematics that are still dominating the however small systematics you have. The question is whether that is, by imposing, of course, whether the two rate be equal, right? I wonder whether there would be enough correlations that can help you pushing down even further your uncertainties.
So I think, what I wonder is if you could actually, so the problem is that I wonder if you could actually extend this B-jet counting method to the single lepton channel. I'm not sure, because then the problem is that the dilepton channel is not sensitive to jet-related uncertainties completely. But in the single lepton, unless you figure out a clever way to get rid of them, you will not get a cancellation, I think. So to my mind, I think this is a bit more complicated, that it's not so trivial to achieve this cancellation effect in the end.
You had a question? Not anymore? Yeah, please. You can also state your name and institute.
Name and institute. I'm Case Benkendorfer with Harvard. I think this is a set of very nice results, of course. And I'm just wondering if you go back to the comparisons between the DR, DS, and the data and the differential measurement. You make this assertion that the differences between DS and DR are inconclusive, but looking visually at this plot, it seems like the DS result is consistently better than the DR result. So I'm just wondering, what is the source of your statement that the differences are inconclusive if it seems that one is actually better than the other?
I mean, my statement comes from the fact that when you look at the error bars, which the error bars on the points are on the theory predictions, and then you have the band on the data. Like, yes, strictly speaking, the central value is better, but both results are compatible within the error bar. So I'm a little bit careful with making this kind of statement. The other point is, okay, I should emphasize that here we're looking at one specific observable. Of course, if you look at a different observable, you don't necessarily get the same conclusion. I mean, in the end, what we see is that you look at one observable, DS is better. You look at a different observable, DR is better. So maybe I should emphasize that you always have to be careful with these conclusions also at what observables you look at. That's why I'm a little bit more careful on the statements.
Thank you.
Did you have one earlier? No? Okay, then
I can maybe add to that. That there's also in the paper there's a quantitative chi-squared comparison of the different distributions, which takes into account both the experimental uncertainties, how they're correlated between bins, and also the theoretical uncertainties from PDFs and scale QCD scale variations. And although yes, in this distribution ds gets is favored, gets a smaller chi-squared, the DR is still acceptable. Inclusive observables like this, the lepton-PT, also kind of bring in other uncertainties, like the basic modeling of the PT spectrum. We've seen that's very sensitive to how you treat the higher order corrections. So, yes, there is some sensitivity, but it's not really enough to make a conclusive statement.
There was something in the back before we go to Andreas. Yes, please.
Hello, I have a comment on your YT modification. So since this coupling does not exist in the tree level, no, the 𝑡𝑡ঁ one.
This one?
Yes. So I think here you can once you modify the YT, you cannot exclude that you are capturing the quantum correction to the 𝑡𝑡ঁ Higgs vertex next leading order. I think you should, okay, this means that one needs the next leading order standard model correction for this. Because basically for me, this is next leading order mixed standard model and BSM correction you are trying to capture. I'm not sure if my comment is clear.
I don't think I fully understood. So
you have the electroweak loop,
yes,
and you introduce the 𝑡𝑡ঁ Higgs YT Yukawa here, and this is not present in the tree level. So start appear at the one loop level.
Yes.
Then you are adding the modification as a EFT approach, which basically says that you are capturing the higher order effects also appear here. So you could purely capture the quantum corrections here from standard model. So I'm saying that you need, okay, theory needs the next leading order electroweak for this, such that it's more under control.
What you're saying is that, let me see if I understand. So what you're saying is that we could also look at these effects in 𝑡TH final state, or like through higher order corrections, or did I misunderstand?
No, I mean, here you profile you try to capture how YT can deviate from 1, but this could be just missing of quantum corrections in the standard model.
Okay.
Andreas?
Thank you. Andreas Meyer, also DESI, but CMS. So first of all, congratulations. It's really impressive. I think it seems very, very well executed. I still wanted to challenge you on two things. One is this modeling of the PT shapes, and going from 0.6% in the previous analysis to 0 is, of course, a radical step. How do we know that next leading order is now describing PT? Because in the plots you showed, there still seems to be a trend.
Yes, so two comments here. One is that the plot that I showed with the PT, you don't see the effect of the uncertainties on the prediction itself. The second thing, yes, here we removed, so this top PT reweighting uncertainty, actually, this was done by comparing the NLO QCD POWEC PTIA with the same generator where we reweighted to fixed order next to leading order QCD. So now that we have the next to leading order QCD prediction itself, this uncertainty doesn't make sense anymore. But that doesn't mean that there aren't any other uncertainties on the NNLO prediction itself. Like you have the scale variations and a suite of other uncertainties that actually should cover for the residual discrepancy that you see between the slope in data and the NNLO prediction.
Okay, but I think there's no evidence that we are actually modifying the shape in PT by scale variations, right? That's always been the problem with the NLO, at least, that
okay, I mean,
scale variations actually did nothing. They only changed the normalization, but not the shape. So as a result, we reverted to this
reweighting method, which was poor, but...
Okay. I don't remember from top of my head how the shape of the scale variations look, so I can't really comment there, but no.
The other thing I wanted to ask quickly is about the...
I think Richard had a follow-up on this.
Sorry? Say again.
Yeah, if you want me, I can maybe comment a bit further. So there is a small scale dependence when you do the scaling variation also on the NNLO Monte Carlo. The other thing we have now is that you can also take the old approach of taking the NLO plus PS Monte Carlo and reweighting to this NLO plus fixed order prediction. And there you get a very, very close answer, a very, very similar answer to using the min-lobs prediction. So I think the min-lobs prediction within its uncertainties is compatible with the data. The other thing to maybe remember is you don't need to model the PT shape perfectly. What's important is how you model it around the threshold, because you're basically using this to extrapolate to the region that you don't measure. So what's happening up at several hundred GeV is not so relevant.
Right. So I think you showed it on page 26. So there the NNLO seems to be a little bit shifted. So the question, it's hard to judge how big the impact is on the measurement if it wasn't. If
you can't really see it from here because the impact of the measurement will be here in this region. It's basically what doesn't come into the plot, right? Through acceptance effects.
Right, okay. The other question I had was about the last statement you made about the treatment of toponium in the Yukawa coupling measurement or extraction. It was a bit surprising that you said that there's hardly any effect on the result with or without toponium. And also, I mean, these toponium models are, of course, to be taken with a very large amount of salt.
So, two comments here. I mean, I won't lie that we were initially also surprised, but we did a huge amount of studies. So first of all, here in this analysis, we take 100% uncertainty on a toponium. So you take the full difference between having the model in there and not having it at all. When we look at the impact on the uncertainties, it's subdominant. And the reason is because that you can't really see it so well here, but the toponium contribution kind of disappears around 400 GeV. Whereas the Yukawa variation has this long tail all the way to like 1 TeV range and further. So what you see is if you compare the shapes in detail, they're really different. So there is no strong correlation between the shape effect of the YT variation and the toponium variation. And regarding the models, I agree that they should be taken with a grain of salt, but we actually compared I think like 3 different models. They're all approximations, but like with different widths or a different treatment where we didn't use this model, but we reweighted the MTT bar spectrum based on a different prediction, and the conclusion was always the same. So we're fairly confident that in the end, in this case, it doesn't really matter that much.
Then we have a question from the outside by Evan Rankin.
Hi, yeah, I had 2 questions actually. My first question regarding the cross-section measurement. You mentioned that you had the lepton ID efficiency uncertainties down to about 0.1%. Something we've seen in CMS is that the lepton ID efficiencies can also vary a bit as a function of the jet multiplicity events. And of course, if you're deriving these from Z plus jets events decaying to EE or mu, and then applying them to TT bar events, you have a different event topology, so a bit of a different N-jet multiplicity distribution expected. We typically have an extra uncertainty to try to cover this. I'm wondering if you looked at that effect, because this seems really precise for the lepton IDs.
Okay, I believe I cannot comment on myself on this. I don't know if Richard has any answer.
Yeah, so the lepton ID itself is always done for isolated leptons where there are no jets nearby, so we suppress the effect of any nearby jets. For the isolation part, which is quite sensitive to the topology immediately around the lepton, then this is why we have these dedicated measurements of the isolation efficiency in TT bar events. Yes. And indeed, it is different there in Z events and TT bar events, and we measure it in situ.
Okay, so essentially that's mostly coming from the isolation, you think, and then that would make sense then that you measure it in C2 and TT bar. Yes. Thanks. My second question might devolve into more of a comment. It's about the top Yukawa measurement. You mentioned the Hathor corrections on, I think, a few slides earlier. That these are corrections that are derived, comparing leading order QCD to essentially leading order QCD with the allowance of one, electroweak coupling, sort of. Then these have to be applied to a next to leading order sample, of course, and of course we can't generate the full electroweak corrections on top of NLO QCD. I flipped through the paper a little and I see that there is an uncertainty associated to this electroweak correction application method. I don't think this is a huge deal because it seems that there's other large sources of uncertainty affecting you, but this uncertainty is effectively proportional to the size of the electroweak correction, meaning it varies as you vary the top Yukawa coupling that you put in. And I see in the paper that this was derived by fixing the Yukawa coupling equal to 1 to the standard model value.
Yes.
I would argue that that's a very optimistic way to define this uncertainty. I think most of the effect of this uncertainty comes from when you try to set the limits and the Yukawa is allowed to.
So we did test this also for yt equal to 2, which is closer to the upper limit itself. But I don't remember the exact numbers, but we found that it didn't matter that much either way in there. Of course, the effect changes. But the choice of the value is, you run into a circular problem. Of course, we set the limit, it's yt2. So now we say, okay, we should do this uncertainty with yt2, and then you get a different yt limit. I understand that there is an assumption you have to make simply because we cannot, or at the state of the analysis, we were not able to include a nuisance parameter that depends on the point of interest itself, basically. So.
Okay, I think it wouldn't affect maybe the total results so much because I see you have other large sources of uncertainty that I haven't had time to fully understand the effect of. But I would say that in the CMS results, we do this dependence of this uncertainty on the parameter of interest, and we saw that including kind of creates a fuzziness around the parameter of interest that does affect the total precision a bit than you might expect. So it's something to watch out for.
Okay, thanks.
Please.
Yes.
Thanks.
So Fabio Maltoni, Bologna. So I have two questions. Well, first of all, congratulations to the impressive series of results on TT bar. So the first one is on the inclusive cross-section and differential. So do I understand well that when you do the study at the inclusive level, you use 1B jet and 2B jet mean, right? Mm-hmm. But when you go differential, you only focus on the 2B jet.
So this depends on the measurement. For the TT bar to EMU differential cross-section, you still use the B-jet counting method extended to the differential case. It's only for the EMU BB differential cross-section where you cannot use this. So there you focus only on the 2B region.
Okay, but I mean, when you say that you study, for example, this DS and DR ski dependence, right? I mean, the 1B jet mean do you use it or not?
No, in this case, you only look at 2B jet events. For the EMU BB case, so in the results, for the EMU BB case, these results are extracted only from events with at least 2B jets, basically.
Yeah, but then you lose, you lose the information from the 1B jet where the WT is dominant, and then you don't have then normalization information, right? Somewhat, if you compare with the usual WT and TT bar sample addition, so to speak, and then you check the interference between the two, from the 1B jet beam, you get most of the sensitivity on the normalization on WT, and then if you only focus on the 2B jet, you are losing that constraint. So I don't understand very well the logic. How can you claim that you somewhat are sensitive to the DRS difference if you don't have a point in your analysis where you normalize TW, or you better normalize it?
But the interference comes to play in the 2B region, because the whole interference comes from the TWB, right? So if we look at 1B region where TW without the extra B jet is dominant production, I think this is the region where you're not sensitive to this.
Yeah, but
and regarding the normalization, I'm not sure I follow the argument, because the data is what it is, right? You unfold, it's bin by bin unfolding, quote unquote, but you measure the cross section, and then you take the predictions at the best predictions that you have, but these are theory predictions. I don't see where the normalization argument comes to play then. Perhaps I misunderstand.
So maybe you can take it.
Yeah, we can take it offline. I have a second question on the Yukawa.
Mm-hmm.
So, I wanted to know the prospects for extending this measurement also to cases where the scalar is beyond the standard model scalar, or you can vary maybe the coupling type, like scalar or pseudoscalar, and the different masses. Because if I remember well, Arthur was missing one diagram.
Yes.
Right. Okay.
Yes. So so a few comments on this. So first of all, it's true that in this measurement we assume we don't assume any CP odd extension of the Yukawa. Yes, Hatter is missing this S-channel Higgs exchange diagram, which actually, I recall that this diagram is very important when you look at the CP odd extensions. For the CP even case, it doesn't really matter. So if we were to extend this to CP odd, we definitely need predictions that include this. We have them, but the larger challenge with extending this to CP odd is, we've done some preliminary studies on this, so I can't really say too much, but you get challenge with the sensitivity, because actually the pseudoscalar variations of like a CP odd Yukawa they have a different shape effect, but they go in the opposite direction. So purely from MTT bar, it's challenging. If you try to constrain them simultaneously, you get this large degeneracies. One possible extension, I believe, would be there is also a angular dependence on a top quark scattering angle. The challenge there is that this dependence is basically non-existent in the threshold region. It only becomes pronounced at very high invariant masses. So you could possibly do a measurement where you, target the boosted regime to get sufficient acceptance. But I think you still face the fact that, the mass goes down exponentially. So the question is if we can get enough sensitivity by trying to look at angular observables at high mass to get another degree of information. But yeah, I can't say much more. But I think it is interesting, but it is challenging.
Okay, so we will take the last two questions. Please, one question each. The first is from outside, Konstantin Charko.
Thank you. It's another question from Daisy. I wanted to get back to the lepton factors, if I may. So yes, comparing the previous analysis with the current one for the inclusive cross-section measurement at the page 16, I also see that the electron efficiencies uncertainties were strongly decreased. What exactly is different with respect to the previous analysis? Because as I understand, both of them use Z into the lepton region, tag and probe, right? But is it just better modeling, or it's because of the decorrelation to lepton PT and the eta? Could you please a bit clarify?
Is the second thing. So in this analysis, the treatment is refined that we take the correlations fully into account in PT and eta across the whole measurement. So you use this, we have like a pseudo-experiment-based replicas to do this, which it wasn't done in the previous measurement. This is by far the biggest improvement there.
Thank you, and congratulations on the result.
Hello, Yoav from University of Chicago. So thanks a lot for the very nice talk. So just a quick comment about the toponium. So we do have recently available a model with lepton+jets, which involve actually the non-relativistic QCD calculation, but this should be only in future. Obviously, it wasn't available for this analysis, so we expect to use it in the future, hopefully. And then, sorry if you can come back to slide 16.
Okay. Oh, what did I
have a very quick naive question there, maybe. So, okay, clearly the dominant uncertainty here is the luminosity, right? But what we have as an uncertainty for the luminosity in Atlas is actually 0.83%.
Yes.
But the values here are bigger, so why? What do I miss here?
So the reason is because the luminosity doesn't enter only in the cross-section, but it also enters through the backgrounds, right? So in this formula, you will get the 0.83 here, of the luminosity factor, but you also have background. And the dominant background is TW production, which is normalized based on theory prediction. So there you also have sensitivity to luminosity. So in the end, effectively, your total luminosity uncertainty is roughly like 1.1 times the actual number on the luminosity calibration. That's why it's bigger.
Okay, thanks.
Yeah.
Okay, so I think we should thank Oliver again. And thanks to you for attendance and the lively discussion, and we see each other next week.